Hi, Honors Algebra. This is 1.6 Day 2 notes. And if we look at these examples A, B, and C, before we actually approach them, I want you to look at this little warm-up that I did on the side. So if you want, you could put this on your paper, or you could just watch to explain more or less what the importance of these signs and the symbols mean and how it's going to differentiate from the next problem. So this tends to be, absolute value of inequalities tends to be the more difficult topic with students find difficulty with, but I'm going to try and clarify that with this little explanation here. So if we take a look at this problem, it says the absolute value of x is greater than 2. Now recall from yesterday's lesson that we just did say that the absolute value represents the distance away from 0. So if that's the case, then I'm telling you that this x value represents all values greater than 2 units away from 0. So all of my x values greater than 2 units away from the 0 on this number line, 0 to 2 is 2 units, but to be greater than 2 units away, that's all of these units over here that are greater than 2. Or there are also all of these units here that are less than 2. Because again, this 0 to 2 is 2 units away. So all of these units to the left of negative 2 are also have an absolute value greater than 2 units away from 0. So we actually can write this by separating it into 2 different inequalities. So I could write exactly how it's written here, just without the absolute value bars. So my solution would be x is greater than 2, which is all of these solutions here, which is x, all values of x greater than 2. Or it could also be all of my x values, which are less than negative 2. So notice that the inequality sign flipped, and so did the number that we just flipped and made it the opposite of 2, which is negative 2. So this represents the answer to all of these, all of the absolute values of the numbers that are greater than 2 units away from 0. Now, the reason we put the word or is because we had a greater than symbol here. So if it's a greater than sign, or if it's a greater than or equal to sign, then that determines that our word in between these 2 inequality statements is the word or. Okay, so if we were to write this in set builder notation, our answer would be the set of all x values such that x is greater than 2, or that x is less than negative 2. And that would be our answer. If we were to write this in interval notation, well, then we read it just like left to right. Our lowest number is negative infinity all the way through negative 2, but not including it, so it's an open interval, united with 2 all the way to infinity. Of course, that's an open interval as well. So that would be our final answer. So that being said, let's go ahead now and take a look at example A. Notice that I have a greater than symbol. So if I have a greater than symbol, or I have a greater than or equal to symbol, that means I'm going to write the or phrase. If I have a less than or a less than or equal to symbol, then that means I'm going to be writing an and phrase. And we actually don't reach this until problem B here, so we'll deal with that in a little bit. But right now, because this is an or statement, we know we're going to have 2 separate inequalities. So we're going to go ahead and write this inequality without the absolute value bars. So just like the original, x plus 5 is greater than 2. And we also know that we have to write another inequality that's x plus 5 less than negative 2. Just like we had to flip the sign here. And this was the whole reason why. Because it's 2 units away from 0. And we can have that happen on the right side of the graph or the left side of the graph. Therefore, both sides of the graph. Okay? So we're going to go ahead and solve this like we normally would, which is we're going to solve for x. So if we subtract 5 from each side, we're going to get x is greater than negative 3. So there's one solution. And if we subtract 5 from the over here, in this inequality, we're going to get x's less than negative 7. So if we were to graph that, since it's an OR, we want both of them. So we have negative 3 and negative 7. So if we graph this solution first, all of my x values greater than negative 3, but not including it, are in the open interval going to the right. And all of my x values less than negative 7 are open interval at negative 7 going to the left. So that is our answer graphically. And again, if you wanted to write set builder notation, or let's just do interval notation, I believe the book just asked for that. It would be from negative infinity to negative 7, united with negative 3 to infinity. So that's our answer for problem A, 2A. All right, now, if you look at B, we have a less than or equal to symbol, which means right away, because it's less than, that tells us it's going to be an and phrase. So that means all of my values, absolute values of x are going to be less than or equal to 7 units away. And the reason it's an and is because on a number line, if we were to just grab 7 units and negative 7, if it has to be less than 7 units away, well, that's everything between 7 units and everything between 7 units on this negative side here. So anything that's between negative 7 and 7 is actually a solution, okay? But now that's just the general, if your graph was the absolute value of x is less than 7 or equal to, okay? But let's go ahead and do this practical, our real example here. This was just a little tip to show you and guide you how to do that and why it is the way it is, why it's an and. So if we were to go ahead and do this, we know that without the absolute value bars, we're going to split that into 2 separate equations. Again, without the absolute value bars. So inequalities, 2x minus 3 is less than or equal to 7. And we're going to do another one, which is 2x minus 3 is greater than or equal to negative 7. So notice that we flipped not only the inequality sign, the direction of it, but also we made it the opposite of 7, which is negative 7. So we're going to go ahead and solve. If I add 3 to both sides, I'm going to get 2x is less than or equal to 10. Divide by 2, x is less than or equal to 5. And when I solve over here for this inequality, if I add 3 to both sides, we get 2x is greater than or equal to negative 4. Divide by 2. X is greater than or equal to negative 2. So I have to graph both of them on the same graph, both solutions. So if this is 0 and this is negative 2 and this is 5, this is telling me that all x values have to be less than 5 or equal to 5, so it's a closed interval. But the constraint also tells me, and it also has to be greater than negative 2 or equal to. So that means at negative 2, everything greater than that, but also less than 5. So that's every value for x in between negative 2 and 5. So this is your and graph here. It's just a solution set, and how we would write that in interval notation is a closed interval at negative 2 all the way up through and including 5. And that's it. Okay. On C, it looks like we can do this problem right now. Notice that this is a less than, so it would be a and problem to start with. But remember, we said you have to have the absolute value isolated first. So right now we have this little neighbor here on the left side of the inequality sign. So we have to get rid of that 12 by subtracting it. So if we subtract that 12, we're going to get the absolute value of whatever's inside is less than -8. Now, if you recall from yesterday's lesson, can the absolute value of any number be a negative number? No, it can't be less than 0. It can't have a negative number because the absolute value represents distance away again. And the distance away is never negative. So this problem can't be done. So it's almost like a trick. So the answer is undefined. All right? There is no negative distance. Okay? So we're done with that. If you look at D, there's a greater than or equal to symbol. So right away, the first thing I would do is look at your sign of your inequality and determine, is this an or or an and? All right, so this is an or. Now, we do have a neighbor here, so we have to have it isolated. So if I divide everything by 2, and again, what you do to one side, you do the other, we do now have x plus 12, the absolute value of that isolated, greater than or equal to 0. So this problem can be done. However, we don't have 0 or -0 because 0 is neither negative nor positive. So what we're going to do is we're just going to split this up into 2, and we have x plus 12 is greater than or equal to 0. But we also have to say, okay, x plus 12 is less than or equal to 0. Well, if we go ahead and solve, we're going to get x is greater than or equal to -12. And if we solve it over here, we're going to get x is less than or equal to -12 as well. But the only difference here, it's an or problem. So if we go ahead and graph this, here's 0, here's -12. All of my x values that are greater than or equal to -12 are to the right in a closed interval, and all my x values less than or equal to -12 are, including it, to the left. So if you look at the span of things, it's all values. So that means it's all real solutions here. So that means it's everywhere. So if that's true, that means the solution is from -infinity to infinity. And that's it for the lesson. And you could now go ahead and do 1.6, day 2. We're going to be going over a question in class tomorrow. So you can start your homework if you want, or just wait for class.